Welcome to Study Loop.
Okay, so we've got the following Newman projection. Oops, this is a 3. Okay. Okay, and what helps me with these is relabeling everything, all the chains, as like a simple name for that chain. So instead of having, say, this CH2CH3, I'm going to just write ET for ethyl because that's an ethyl group, right? And instead of having this 3-carbon chain, I'm going to write little I, big P, little r. That's isopropyl. Iso meaning straight, propyl meaning 3. A straight chain of 3 carbons is an isopropyl. Sorry. Isopropyl is, that's way wrong. I got ahead of myself. It's a little N. N means normal, which means straight. Isopropyl looks like that. N-propyl looks like that, right? This is the isopropyl attached to carbon 2. This is the N-propyl attached to carbon 1. Okay, so that's an N-propyl group coming off the side. The reason for that is that now I can kind of do what you do with Newman projection problems, but in reverse. Like I'm going to draw a sawhorse, right, with a bond up, a bond down, wedge, dash, wedge, dash, and then just copy what I see. Like let's call this carbon 1, call this carbon 2. So we got carbon 1 in the front and 2 in the back, right? Actually, maybe it'll be easier. Let's call this carbon 1 because we got. I changed that because in this Newman projection, the front carbon has a substituent facing up, whereas the back one has it facing down. So I wanted that to match here, where this substituent is facing up and this substituent is facing down. If you're wondering why I changed that midstream, that's what's going on. Okay, so then I just matched this up, assuming that I were looking down that bond, right? So I'd have a cyanide straight up at me, right? What's to my left? It's this H3CO. So this is my H3CO. All right, and then let me move this I out of the way. What's going to the right? It's this ethyl group. Right? Great. Now I consider the back. I know that down we've got this hydrogen. And remember, we're looking from this point of view. Up and to the left is the N-propyl. And up and to the right is the hydrogen. And that's pretty much it. This is the bond line structure. If I want to change this to maybe a more proper bond line structure, all I've got to do is redraw it without the N-propyl and the ethyl, but instead just having legitimate chains. And we could do the same for this ether linkage here. So let's do that real quick. There's our cyanide cyano group. Okay, then we've got a wedge to an oxygen that has a methyl sticking off. And we've got a dash to an ethyl group as follows. Great. Then we've got a bond down to a hydrogen. Typically we wouldn't even draw that, but that's fine. We've got a wedge to this N-propyl. So 1, 2, 3. And we've got a dash to also a hydrogen. Okay, now when we look at this, we might notice something. This is not a stereocenter, right? Because we've got 2 hydrogens there. So it doesn't matter how we draw that. It's really inconsequential. In fact, the only stereocenter in this molecule is right here, which I'll label in green, right? So let's determine what the stereochemistry of that is so that we can redraw this in a more standard fashion, where we're going to draw a bond line drawing without any wedges or dashes except for on the green carbon, right? That's kind of what we're used to seeing when we're talking about stereochemistry. We're not used to having just this one bond highlighted, right? This isn't like a typical bond line drawing. This is the sawhorse projection, so we're trying to move out of the sawhorse projection. All right. So, what is the stereochemistry of that green carbon? Well, we've got to assign priority to all our groups, right? Oxygen, this bond to oxygen is going to be the highest. Next would probably be this carbon with 3 bonds to nitrogen. Then we've got to decide between this is a CH2 with a 2 carbon chain coming off of it, and this is a CH2 with a 3 carbon chain coming off of it. So it sounds to me like the CH2 with the 3 carbon chain off of it is going to be higher priority. So this will be the 3rd highest priority, which will make this ethyl group in the back the 4th highest. So now we've got, thankfully, the 3 highest priority groups in the front, which means we can simply determine clockwise or counterclockwise between those 3 groups. I see 1, 2, 3 being counterclockwise, and quickly ascertain that this has S, stereochemistry. Okay, so we really just need to draw a 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon chain. Is that 1, 2, 3, 4, 5, 6? Oh, I've drawn too many carbons. Sorry. That should not be a carbon, and that should not be there. I messed up when I was translating the ethyl and the isopropyl. That's okay. Point still stands that nothing else changes. I just drew too many carbons on the end of either of those. So we have a 7 carbon chain, right? And on carbon, maybe 1, 2, 3, we've got a stereocenter, right? So let's start with a 7 carbon chain. 2, 3, 4, 5, 6, 7. Right, and on carbon 3, that's our green carbon, we have an S configured cyano and methoxy, basically. Right. So once when I get into a situation like this where I've got to draw the S configuration, I actually just guess and then check it and then see if I drew it S or R. And if I drew the wrong one, I just swap the 2 groups. Right. Okay. So is this S or R? Let's label the priorities 1, 2, and 3. And recall that since the lowest priority group, in this case this ethyl, is not in the back, that whatever we determine the stereochemistry to be by following the priority 1, 2, 3 as clockwise, if the highest priority group is not in the back, it's the opposite of whatever it looks like. So it looks like R because it's clockwise, which means it's actually S, which means we guessed properly. We don't have to redraw it. So this is in the S configuration already. Great. So this is this matches the Newman projection. Now, if we want to draw the enantiomer, all we've got to do is swap any of the 2 groups at carbon 3. So I think the most straightforward things to swap would be the cyano and the methoxy. So let's do a wedge to our cyano and a dash to our cyano and a wedge to our methoxy. And that's our answer. This is the bond line structure. Bond line. And this is our enantiomer.